Good morning, good afternoon, or good evening. This is a full question work through for the 2024 Step 2 paper, and we're now looking at question 4. As always, if you are attempting these step questions yourselves, you should be giving it a real good effort before looking for any hints, solutions, etc. So you should only really be watching this video if you've already completed the question and you want some other insights into another way of tackling it, or you've already given it a good hour or so and you're looking for some hints. And good advice if you do receive a hint that's giving you that one step forward, pause the video, go try and follow that hint through yourself before coming back and watching how it worked. Now hopefully we're going to tackle this question successfully. This is now question 4, still a pure question within the 2024 paper. And again, quite a classic style. We have, to start this question, a new definition. In this question, if we've got non-collinear points in 3D space, we're going to call a vector a bisecting vector of the angle if it lies in the plane COD and the angle bisects the OCD angle, and both angles are less than 90. Okay, so a couple of things to kind of break down there, and it's worth considering all this before you really start the question. We have 3 points. Now they have to be non-collinear. If they're in a straight line, then we won't have an angle that's interesting. We'll bisect it and it'll be more of a perpendicular bisector style thing. But we have this setup, and I've drawn the big parallelogram to kind of represent the plane, and we're looking for this vector this vector V, so that it bisects that angle there. Is the same as that angle there. We've cut the angle COD in half. Now I did pause while reading it briefly when I saw both angles are less than 90. Well, that's to prevent us from using this angle, which will be negative V, because then that angle there and that angle there would be the same, but they're now obtuse. They're now bigger than 90 in both cases. So we're always going to choose to pick the angle to make it smaller. Straight away, my mind is going towards the the dot or scalar product, because OC dotted with OD is equal to mod OC mod OD cos of the angle between. So we're looking to cut this theta angle in half. And another good trick to know is if we want this theta to be less than 180, well, really, if we want this theta to be, how is it going to work? The cos, yeah, the angle between these two vectors. Yeah, if we want this angle to be less than 90, then the OC dotted with OD is positive. And we could probably just force that by taking the modulus of OC dot OD when we do this calculation. And that just enforces that we're pointing in the right directions. Maybe relevant, maybe not. So let's actually start continuing to read the question. We've got this definition of a bisecting vector now. Let O, X, Y be non-collinear in 3D space. We're going to find little x to be the position vector of the point X, little y to be the position vector of the point Y, and we're going to let this be this weird combination. So it's the size of X times the direction Y plus the size of Y times the direction of X. Show that B is a bisecting vector for that. So we need to show that the angle between B and X, so again I'll probably just draw the picture here. We have O, X, Y, we have that vector is little x, that vector is little y, and we've got a vector here b defined to be mod x y plus mod y x. So we need to show that the angle between x and b is the same as the angle between b and y. Show that b is bisecting. So let's try that. So let's say that this angle here is theta and this angle here is phi. So then cos theta is going to be, well, it is x dotted b over mod x mod b. Now this mod b is scaring me a little because b is a weird combination of x's and y's, so I'm probably going to leave this mod b as a mod b and hope it appears in both cos theta and cos phi. But the numerator we can at least deal with. So the numerator is going to be mod x dotted with y, x dot y plus, and then mod y, and x dot x is just mod x squared over mod x mod b. I've used the fact there that I've used multiple facts. I've used the fact that the dot product is distributive over addition. I can expand the dot product over a bracket, and that x dot x is mod x squared. So now we've got a mod x in common, so that's x dot y plus mod x mod y over mod b. And now this is really promising because there's nothing about this answer which was special about x. I used the vector x to create this, but x and y are symmetric. So if we do a similar thing, so cos phi is y dot b over mod y mod b, which again, if I expand out the numerator, that's mod x, y dot y is mod y squared plus mod y, y dot x over mod y mod b, and that's going to be the mod y cancels, so that's mod x mod y plus y dot x over mod b. So cos theta equals cos phi. Now we do need to be a little careful because we have to have this condition that both angles are less than 90. Is that worrying? We would quite like to show that both cos theta and cos phi are, well, they're both the same, but they're positive. And, well, we need to be careful. So let's just make sure that we're not going to lose. We'd lose a reasoning mark or two if we don't justify this. So let's notice that the mod, and this is a general result, mod of y dot, mod of x dot y is mod x mod y mod cos of the angle XOY, but cos is always less than 1. Well, it's between 1 and minus 1, so mod is less than or equal to 1. So that's less than or equal to mod x mod y, which really means, well, the smallest, because we're talking about moduli here, this is between negative mod and the positive mods, which means that x dot y plus mod x mod y is always greater than or equal to 0, which means that cos theta is always greater than or equal to 0, i.e. theta, the principal value of theta at least, which is all we really care about here. 0 is less than or equal to theta, less than or equal to 90. Okay, so now this, I probably should have finished this line of logic here. This means that theta equals phi, at least the principal value, and because we're only working between 0 and 360 and we're pointing all in the same directions, we could have 360 minus theta for each of these, but then we're measuring round the wrong ways. Theta equals phi in their principal values. So thus B is a bisecting vector. Nice. So we've taken the definition and we've checked their definition very carefully. Now part A does have a second comment in there. Explain using the diagram why any other bisecting vector is a positive multiple of B. So you already have this picture up here. So this we can call, I'll call this vector A. So if A is a bisecting vector, then, well, it's in the same direction of B. B is defined to have the direction by being a bisector, then A is parallel to B, so is a multiple. Now it also has to be a positive multiple. Well, if it was a negative multiple, it would be pointing the other way, and we break the less than 90 condition. As the angle, as the angles are less than 90, A must. Now, what's the best way to say this? Must be in the same direction rather than the opposite direction. Must be in the same direction as B, which implies it's a positive multiple. Hey, nice. Part B then. Find the value of lambda such that the point B, defined by a multiple, lies on the line xy. Okay, so we've got the direction of our bisecting vector, but now we want it to lie, we want to complete the triangle basically. So we have OX, OXY, we have that being in the direction of B, and now we want this special point here. Okay, so how are we going to find this? Well, this is kind of our simultaneous vectors idea from GCSE level, really. So we can say that OB is a multiple of B using the notation they've given, but also we can say that OB is X plus some different multiple of x to y. Now x to y is y minus x. I'm actually going to put in what I know b is, mod x y plus lambda mod y x. So now we can read off two simultaneous equations basically. Looking at the y coordinates, lambda mod x equals mu, and looking at the x coordinates, lambda mod y equals 1 minus mu. So we don't care about mu. Mu is something I made up. So let's eliminate mu. So lambda y equals 1 minus lambda x. So then lambda is, if I rearrange this, is 1 over mod x plus mod y. Find the value of lambda, yada yada, sorted. Now it's worth, just because it looks cool, writing what OB is. OB therefore is mod x over mod x plus mod lambda plus mod y, lots of y, plus mod y over mod x plus mod y x. And the reason I wanted to write that out is just to observe how symmetric it is. And almost always these things are beautifully symmetric. Part C. Now I do have enough space here. Part C. Show that in the case when OB is perpendicular to xy, well, being perpendicular says the dot product is 0. So OB perpendicular to xy is going to mean that OB dotted with y minus x equals 0. Show that the triangle XOY is isosceles. Okay, well, first let's consider which part of it is going to be isosceles. So we have that this here is our bisecting vector. Those two angles are the same, so it appears that this angle, let's change colour briefly, this angle and this angle will be the equal two angles, i.e. this side and this side are the same. So what we're really trying to show is that that side there, mod x, is equal to mod y. So let's see if this dot product condition does indeed imply that mod x is equal to mod y. So this is going to be quite a large dot product here, and I'm now doubly glad that I wrote down what OB was in the line above. So OB is that I'm dotting it with y minus x. So again, I'm going to use the distributive nature of the dot product. We can expand out brackets in the way we expect to expand out brackets. So basically this is a FOIL between OB's big bracket and y minus x. So the firsts, and again I'm going to use the fact that y dot y is simply y squared. Outsides, so that's minus x y dot x over, I'm going to get sick of writing this fraction in a moment, and we can kind of start to visualize why this fraction isn't needed. X dot y over, because I can just multiply through in a moment, minus, and the final one is y x squared over x plus y. Now I'm already quite happy because most things in here are just mods of stuff. I've got a couple of dot products in the middle, which makes me a little annoyed, but maybe we're fine with that. So this is going to be mod x mod y squared minus mod x x dot y plus mod y x dot y minus. Okay, so I've cleared out the denominators and I've got this nonsense here. What can we do with this? There's no obvious common factor. I could try and factorize something. Yeah, I don't quite have a dot with x in every term. I don't have a dot with x in this first term. I don't have a common factor of anything. I could expand out the x dot y. Is expanding out the x dot y as mod x mod y cos angle going to be useful? Potentially. Yeah, there looks like a lot of stuff will then cancel out if I do that. So mod x mod y squared minus, this is going to be a mod x squared mod y cos, I can't want to give it a name. I've already used theta and phi in previous parts. So let's go with psi plus, this will be mod x mod y squared cos psi minus y x squared equals 0. Now I can cancel out a mod x and a mod y from every term. So mod y minus mod x cos phi. Starting to feel like I'm going to be going around, maybe not in circles, but not getting to an effective point. Now certainly if mod y equals mod x, this holds. Maybe let's do some factorizing and rearranging. That seems like a sensible choice. So on this side, I'm going to keep cos phi mod y minus mod x equals, and if I throw the other stuff over, that's going to be mod x minus mod phi, mod y. Now, did I want that actually on the other side? I feel like I do. I feel like I'm seeing a silly factorization here. So I can then say this is minus mod y minus mod x. And I've got this factorization, cos phi minus 1 mod y minus mod x. And through this whole set of algebra, I was constantly trying to think, how am I going to get rid of this phi stuff? How am I going to use the conditions from the very beginning of the question? The beginning of the question said that OCD, or actually OXY, are non-collinear. So let's break down what that means. OXY non-collinear. Well, that means that the angle XOY is not 180, is not pi. So therefore, cos of this angle I've called psi is not cos of pi, is not cos pi, but cos pi is -1. So therefore, cos phi plus 1 is not 0. Oh, I was hoping. Oh, I've got a sign wrong over here. Yeah, that should be a plus there. That should be a plus here. So cos phi plus 1 is not 0, which means we can cancel that bracket out. So that means that mod y minus mod x is equal to 0, namely that mod x is equal to mod y, i.e. OXY is isosceles. I've missed out part of the word there. Is isosceles. So once again, this is quite a useful thing to have in your mind the whole way through. How are the conditions of the question actually going to help us in the question itself. This felt like we could have just smashed our face into this algebra an awful lot, but noticing this condition and noticing that we can factorize that condition in a clever way turned out to be exceptionally useful. I'm not claiming this is the only way, and you and other solutions are likely to have found other ways to do this as well. Okay, that is, however, all of part I done. Let's just kind of reflect on what we have done there. We've worked out the shape of a bisecting vector as mod xy plus mod yx. We found that we can scale it to make a triangle, so it lies on xy. And we've also considered how that triangle could be isosceles, and how isosceles is actually equivalent to being perpendicular. The bisecting vector is perpendicular to the base side. So how are we going to use that in the final part of the question? Let O, P, Q, and R be 3 points in space, no 3 of which are collinear. Okay, well now we actually have a 3D nature here. With only 3 points, we really are only stuck in the 2-dimensional plane. With 4 points, we can actually be 3D. So really now I'm imagining we have a tetrahedron style shape. We have O, P, Q, R. I'm kind of thinking O as the top of my tetrahedron. A bisecting vector is chosen for each of the angles. So we have a bisecting vector in each of these. And now it's incredibly impossible to draw these all and keep the visualization going. Show that the angles between them are either all acute, all obtuse, or all right angles. Okay, so what exactly is this now saying? OPQ are 3 points, no 3 are which are collinear. So I'm in the condition where I can make bisecting vectors. I should probably start to introduce some notation. So let the vector P be the position vector of P, Q be the position vector of Q, and R be the position vector of R. Let A, B, and C be bisecting vectors. Bisecting vectors of POQ. Which order have they written in? QOR and ROP respectively. So respectively. So these red vectors I've drawn. So POQ, this is my vector A, QOR, B, C. And I'm trying to show that the angles between them, so the angles between my bisecting vectors are either all acute, all obtuse, or all right angles. Gosh, that seems like a condition. Well, this is going back to something we said about the dot product and the sign of the dot product. So we want to show that if A dot B is positive, then B dot C is positive and C dot A is positive. That would be the condition where all of those angles are acute. If A dot B is negative, we want to show that B dot C is negative and A dot C is negative. And finally, if A dot B is 0, then the dot products will be 0. So let's comment that at least. So let's notice if all angles between the bisecting are acute, then A dot B, B dot C, and C dot A are all positive, and vice versa. I probably should have said if and only if, rather than just if. And equivalently, they equal 0 if only if all right angles, and less than 0 if and only if all obtuse. Now, how does that help at all? Now we could, I'm trying to think of which method of proof to go for. There might be some contradiction going on here. If we assume one's positive and one's negative, then we get a contradiction of some form. Or to just start with A dot B being positive and trying to force the others to be positive as well. Neither of which sound particularly simple or easy in any way. Can we can certainly say, so let's try that second choice of breaking it down into the conditions. So if A dot B is positive, what does that mean? Well, A is the vector mod P Q plus mod Q P dotted with B is Q and R, so mod Q R plus mod R Q. That's positive. And if I dot these together, do I want to expand these out and see what happens? Because I quite like to have the dot product between A and C pop out, or the dot product between maybe I want to do the equals 0 case first. Maybe the equals 0 case is easier. Let's keep following this through. So this is going to be mod P mod Q Q dot R plus mod Q mod Q squared P dot R plus mod P mod R. Now let's make sure I'm doing every combination correctly. Q dot Q, which is Q squared, plus mod R mod Q P dot Q is greater than 0. Oh, I did have a bit more space. Okay. Now this, it doesn't quite look symmetric. It would be quite nice if it was symmetric, because then I can do a bisymmetry argument and just say it works and factorize it in another way. It doesn't quite look symmetric, which is saddening. Now, we haven't been told anything. We've only been told that P dot Q, P, Q, and R are not collinear. So these dot products are not whatever a mod mod Q mod R. How do we approach? Now these are all if and only if conditions, so that's helpful at least. Now if I did write out B dot C, I would get a very similar thing, but all of my A's been replaced with C, so all my P's would look like R's. No. Something will change, but in a non-obvious way. How can I attack this? Now I could throw in a load of angles. I could change my Q dot R into mod Q mod R cos of the angle between Q and R. That feels too messy. That feels like it's going to be way too messy. I'm going to write out down here just so I can focus my attention on what I'm looking for and what B dot C is. So B is mod QR plus mod RQ dotted with C. C is between R and P, so mod RP plus mod PR. So that's going to be mod R mod Q R dot P plus mod R squared P dot Q. And you can kind of see the link between these two conditions, plus mod P mod Q mod R squared plus mod R mod P Q dot R. So some of these terms look very similar. That term looks similar to this one, with the squared in a different position. And I'm just checking, there is a common factor in this. So this is mod Q mod P Q dot R plus mod Q P dot R, and I'm going to reorder slightly, mod R P dot Q plus mod P mod R mod Q. Oh, and nice. So because O, P, Q, and R are points which are non-collinear, they're also distinct. So that means that Q is not the point O. So mod Q mod Q is non-zero. This is mod P. And now this thing is incredibly symmetric, which is what I was hoping for in the first place. So this thing is greater than or equal to 0. So now B dot C has a common factor of mod R. And R, of course, is the, well, not of course, but R is the overlap. Yeah, R was the overlap between the B and the C, which is why that's a common factor. So it's mod Q R dot P plus mod R P dot Q plus mod P. Again, I'm reordering the terms just slightly, which is greater than, which is just greater than 0 because of by star. And similarly, which one haven't I done? A dot C. A dot C. Come on, pen. Pen's just died. Hold on a moment. well, you can see what happens. I might not be able to complete this proof here because that pen has just run out of power. But you can see that A dot C will have the common factor of P, so that will also be greater than 0. And I don't think greater than 0 actually made any difference here. If I replace that greater than 0 with less than 0, the whole argument would have gone through in exactly the same way. And if I replace the whole argument with equals 0, the argument would have gone through in exactly the same way. So we're done. A little disappointing the pen died right at the end and I'm not able to finish writing down. But the argument goes all the way through. We had this very weird algebraic final steps to this problem. Right. I'm sure you'll be able to complete that proof yourselves without the full working. I'm sorry that the pen did fail right at the end. If you are carrying on with working through these step questions, good luck. And hopefully some more of these will be uploaded soon.